Welcome to this workshop on model-based wireless control using a Kalman filter. In this video, we examine the solution to the workshop contained in Chapter 8 of the book Wireless Control Foundation. This workshop is designed to demonstrate wireless control using a Kalman filter in combination with a PID and to compare that to control using PID and a wired measurement. In the initial part of our exercise, we'll look at the module that is used to create the Kalman filter and how that is used with the PID in wireless control. We'll then be initializing our performance index and introducing a set point change in both wired and wireless control, and then observing the integral of absolute error and number of communications. We'll then reinitialize our performance index and introduce a disturbance in both the wired and wireless control, and then observe the integral of absolute error and number of communications for both the wired and wireless control. In the workshop, we'll be using this module for our exercise. You notice in the upper part we have the wireless control where the wireless measurement is being simulated. The PID is being used in combination with the Kalman filter. The Kalman filter is used to predict the measurement value. The Kalman filter uses the wireless measurement as well as the valve position to predict the value that is then being used by the PID and control to adjust our wired valve. The control using our wired measurement is just an input-output using PID. For both the wired and wireless control, we have identical processes that are being simulated. I have the same gain, dead time, and time constant. For wireless control, we're simulating windowed communication in which the dead band is 1%, the period is 8, and the default time is set to 16. The Kalman filter composite that we're using is normally predicting the measurement value based upon the valve position and the user entered gain and time constant. So those are used in the prediction. But if we get a new measurement value, we then compare the predicted value to the measured value, and then the error between is used to update and modify the prediction. The Kalman filter can be implemented on most DCS systems using the normal calculation blocks that are within that system. The simulation that we'll be using for the process for both wired and wireless control is shown here. We're simulating the process as a dead time of 2 seconds, a gain of 1, and a time constant of 6. The tuning of both the PID used in wireless and wired control is based upon that. The gain of the control is 1. And the reset is set equal to the process response time, or 8 seconds. So that is used in both control using the Kalman filter and control using a wired input. At this point, we're shifting over to the module being operating online with a set point of 50%. As you can see, both the wireless control and the wired control are at set point. The performance is being calculated using our performance block. We can initialize that to a value of 0 through a reset parameter, and that's what we've done here. We're now allowing it to perform its calculation, and to demonstrate wireless versus wired control, we'll introduce a set point change. In response to a set point change, we see both the wireless PID and the wired PID immediately change the valve position, and in response to that, our simulated process is showing the actual measurement starting to change. This is better visualized by looking at a trend. Here we see the set point change, the step change, set point. The smooth change that we see here is due to the wired measurement using PID. The stepwise change in our measurement is the wireless measurement that is used in control, and the predicted value is then used in the actual adjustment. So we see a smooth change in valve position even for the wireless control because we're operating in between new measurements based upon the predicted measurement value. We'll now change the set point in the opposite direction and look at the response of the control going in the other direction. Again, we see immediate response in the valve for both the wireless and wired control. And we see some difference in terms of the way the valve is being adjusted. And also, we definitely see a difference in terms of the measurement. With the wireless, we only see a measurement update every 8 seconds. So we see a stepwise change in our measurement. But our control with the Smith predictor is based upon the predicted value, so we see a smooth change in the valve even with the wireless measurement. Over time, you notice that the valve position for both the wireless control and the wire control end up at the same point, and we achieve a set point both for wired and wireless control. If we compare the performance, we notice that the performance of the wireless control is a little bit worse than the wired control, which is what we'd expect. But the number of communications used in wireless control, we only use 10 new measurements. And yet on the wired we used over 200 measurements in doing the control. So by combining the Kalman filter with the PID, we're able to handle wireless measurements using very few new communicated values. To examine the control that we would see for a disturbance change, we have initialized our performance index back to 0, and we're going to introduce a change in our process, an unmeasured disturbance. As we can see here, as the measurement starts to change to reflect the disturbance, then the PID used in wireless as well as wire control must now do its work to bring the process back to set point. As the measurement starts to change, we see both the wireless and wireless control start to change valve position. We see a little bit of a delay in terms of the response of the wireless control because we're only updating the measurement every 8 seconds, and therefore only when we see the change through the communicated value do we then start to take action. But over time we notice that the valve positions become equal for wired and wireless, and both the wired and wireless control come back to set point. We'll now change our disturbance in the opposite direction to observe control performance going in the opposite direction for an unmeasured disturbance. Again, we notice that there is some delay in terms of the wireless control due to the fact that our wireless measurement is only updated every 8 seconds. And the disturbance could have occurred in between measurement updates, and therefore we must wait until we get a new measurement update to see the impact of the disturbance. However, over time you notice that the valve position for the wired and wireless become the same, and the control parameter for both wired and wireless control is brought back to set point through the control actions that are being taken. If we examine then the performance, we notice again that the wireless control is a little bit worse than the wired control. However, in this case, it only took 11 new communicated values for our wireless control versus over 200 communicated values used in our wired control. So this demonstrates that by combining the PID with a Kalman filter, that we can do a fairly good job of doing control using a wireless measurement, even though the update rate is fairly slow in terms of the update. Now, in the Kalman filter, the user must specify the gain and time constant. In this case, the gain and time constant exactly match what is in our process. If we didn't know that and we guessed at that incorrectly, then the performance would be very much impacted.